In this last video of our solutions unit, we look at molarity and dilution. There are two common ways to describe concentration in a solution. We can have a dilute solution which contains a low concentration of solute, and we can have a concentrated solution that contains a high concentration of solutes. We can see that in our dilute solution, there are lots of solvent particles and few solute particles. In our concentrated solution, we have a lot more solute particles in the solvent. In chemistry, we use molarity to better express concentration of solutions. The molarity of a solution is the number of moles of solute per liter of solution. So we can express this in a formula that says M for molarity is the moles of solute divided by the liters of solution. We must use liters, not milliliters, in this formula. So for example, a 2.5 molar HCl solution means that we have 2.5 moles of HCl dissolved in 1 liter of solution. Now remember, in our gases unit, when we did the airbag activity, we also said that molarity can be expressed as a conversion factor. So here it is again. If we have a 2.5 molar HCl solution, we can put that as a conversion factor and say that we have 2.5 mole HCl over 1 liter HCl, and here's our conversion factor. This may come handy in some calculations later. Let's do a few practice problems using this formula. Find the molarity of a solution that contains 0.35 moles of ammonium iodide in 1.55 liters of solution. So our formula is over here, M equal moles of solute over liters of solution. So the molarity M was 0.350 moles over 1.55 liters of solution, and that gives us 0.226 molar ammonium iodide. Second example, find the molarity of a solution that is made by dissolving 53 grams of potassium chloride into 500 milliliters of solution. So since my formula uses moles and liters, and in my problem I have grams and I have milliliters, so I have to do a couple of conversions first. So I'm going to convert 53 grams of potassium chloride to moles, and we know how to do that. Molar mass of potassium chloride is 74.55 grams, and that is 1 mole of HCl. And I get 0.711 moles of KCl. So now I have my moles to plug into my formula. Then I have to convert 500 milliliters to liters. So 500 milliliters. And I say that 1000 milliliters is 1 liter. And I get 0.500 liters. Now I'm ready to plug into my formula. Molarity equals moles, 0.711 moles, divided by liters, 0.500 liters, and I get 1.42 molar potassium chloride. This problem says find the volume in milliliters of a 3.5 molar potassium chloride solution that contains 47 grams of dissolved potassium chloride. Again, my formula has moles and I have grams, so I have to convert that first. So 47.0 grams of potassium chloride, and I convert that to moles. Again, the molar mass is 74.55 grams of potassium chloride is 1 mole of potassium chloride, and I get 0.630 mole of potassium chloride. Now I can plug it into my formula to find the volume. So I'm going to say molarity, which is 3.5 molar equals the moles, 0.630 moles, divided by the liters. I don't have the volume, so I'll put X here. So I can solve for X. So I can say that 3.5 X equals 0.630. So X equals 0.630 divided by 3.5, and I get 0.180 liters, because it's liters of solution in my formula. But my question asked me to find the volume in milliliters, so I need to convert that to milliliters, and I say 0.180 liters. 1 liter is 1,000 milliliters, and I get 180 milliliters. In chemistry, we often need solutions of various molarities depending on the task at hand. We can dilute a concentrated or stock solution with a solvent, which is often water, to obtain the molarity of the solution that we need. A solution is diluted by adding solvent to the concentrated solution, and that solvent is often water. So if we have a concentrated solution here, which is our stock solution, we can add water to it, and that will produce our diluted solution. We can express this change in molarity with a formula to predict our needs, and the formula is M1V1 equals M2V2. M1 is the molarity of your initial solution, and V1 is the volume of your initial solution. So this is the stock solution or your concentrated solution. M2 is the molarity of the new solution, and V2 is the volume of the new solution. So this would be the molarity and volume of your diluted solution. For the volume for this formula, as long as the volume of V1 and the volume of V2 match in units, that's fine. You don't have to use liters only. If you are preparing 100 milliliters of 0.4 molar magnesium sulfate from a stock solution of 2 molar magnesium sulfate, what volume of the stock solution did you use? And then how much water did you add to your initial solution to perform this dilution? So we have M1, which is the molarity of our stock solution. So that is 2.0 molar. Then we have V1, which is the volume of that stock solution, and that's what we're trying to find. We have M2, which is the molarity of the diluted solution, and there it is at 0.4 molar. You can see it's less concentrated. And then we have V2, which is the final volume of our diluted solution, and that's 100 milliliters. Now we're ready to plug into the formula. We have 2.0 molar times V1, I don't know, equals M2, so 0.40 molar, and V2, which is 100 milliliters. So we solve for V1, and we get V1 equals 20 milliliters. Now the next question says, how much water did you add to your initial solution to perform this dilution? So we can draw a picture there to see what happened. We had the stock solution, which was 2 molar, and we now know that we had 20 milliliters of this solution. And then we added water to this solution, and we know that the final volume of the diluted solution, so all of this was 100 milliliters. So how much water did we add? Since we started off with 20 and we ended up with 100, so the water added will just be 100 milliliters minus our 20 milliliters, and I get 80 milliliters. of water. Now pause the video and try this question on your own to check your understanding. Here are the answers. Please ask good questions in class as needed as we practice those types of calculations. And this is the end of our solutions unit.